At first light in northeastern Wyoming, the tower does not look like rock, it looks cut. A dark cylinder rises alone from the prairie, its sides furrowed in long vertical bands, its top sheared flat as if something immense once stood here and was removed. From a distance, the surrounding hills resemble spoil piled around a stump. Up close, the columns look less like a mountain face than bundled fibers, tightened, mineralized, and left behind. It is one of the most photographed landforms in North America, and that may be part of the problem. Familiarity has made it ordinary, but the shape itself is not ordinary. The scale is wrong, the silhouette is wrong. The first impression is simple and difficult to dismiss. What exactly are we looking at? The accepted explanation arrives quickly. Devil's Tower and thousands of mesas, buttes, hydropinnacles and flat-top formations like it are said to be the products of geology alone. Magma intruded underground, cooled, fractured into columns, and was later exposed by erosion. Elsewhere, sedimentary layers hardened unevenly. Softer rock wore away. Harder rock remained. Over enough time, plateaus became mesas, mesas became buttes, and buttes became spires. This is the standard sequence. It is taught in parks, textbooks, road signs, and field guides. The timeline is vast, the forces are gradual, and the forms are natural. But what happens when the official explanation begins to sound more complete than specific? What happens when the language becomes a category instead of an answer? To say a butte is an erosional remnant is to describe what remains, not necessarily what it first was. To say a tower is an intrusion is to name a process, not to settle every feature of its shape, texture, boundary, and context. At Devil's Tower, even the geological literature has carried more than one formation model over time. Stock, plug, intrusion, remnant. The labels shift, the monument stays the same. And the contradiction remains where anyone can see it. Certain landforms do not merely resemble stumps, trunks, roots, or severed wood. They resemble them with an almost embarrassing literalness. So the hidden theory enters quietly. Not as a rant, not as a replacement for all geology, as an investigative possibility. Some of the world's most striking isolated landforms may not be adequately understood if they are treated as rock first and biological form never. Some may be mineralized remains of organisms or of organic structures, on a scale modern ecology no longer permits us to imagine. Others may be composite forms, biological foundations later altered by heat, pressure, flooding, burial, and erosion until they passed into the map as geology and never came back out. The question is not whether every mesa was once a tree. The question is whether the category landform had, in some cases, concealed a different origin. Begin with morphology. There is a reason the theory keeps returning to the same formations: Devil's Tower, Mato, Tipula, Bear Lodge. The vertical fluting is unusually regular, running from base to summit like grain. Around the tower, the talus field is made of fallen polygonal columns, broken into lengths that look less like random rubble than snapped sections of a once continuous structure. Nearby sedimentary layers bend around the intrusion, which geology explains as deformation from rising magma. Fair enough, but in image after image, what dominates is not the surrounding bedrock. It is the central cylinder, isolated, fibrous, and abruptly truncated. The top is not peaked, it is cut. The form announces itself before any theory does. That matters. Then widen the frame. Across the American West, there are buttes with broad caps, towers with radial ravines, knobs with concentric terraces, and isolated plateaus that stand on plains like amputated columns. In aerial view, some drainage patterns resemble root flares radiating away from central masses in all directions. At ground level, many display a verticality that reads not as layered deposition, but as bundled structure. Even where geology calls the material sandstone, basalt, breccia, or intrusive porphyry, as the visual logic repeats: a trunk, a cap, a weathered apron. The pattern does not disappear, it changes names. Now consider scale, because scale is where normal explanation becomes psychologically unstable. The fossil record already tells us that Earth once supported forests unlike anything alive today. Carboniferous leucopsids reached heights far beyond modern club moss relatives, giant horsetails, vast swamp forests, and tree-sized forms from lineages now reduced to low plants once dominated entire landscapes. Petrified trunks dozens of meters long have been documented. Upright fossil stumps still stand in coal-bearing strata. Coal itself is the compressed memory of forests. The official record does not deny ancient gigantism. It only limits it to sizes the modern mind can reluctantly absorb. But if Earth conditions once allowed vegetation on scales now vanished, what principle says the old upper boundary is already known? This is where critics usually object, and the objection deserves to be taken seriously. Trees, as we understand them, face mechanical limits. Gravity, vascular transport, wind loading, nutrient flow, and tissue strength all impose constraints. Modern redwoods already operate near the edge of what current atmospheres and biology allow. A tower half a kilometre high sounds absurd for a tree. On present Earth, it probably is. But that objection assumes the same atmosphere, the same pressure, the same chemistry, the same growth strategy, and the same anatomy. It assumes that ancient giant life, if it existed, followed the rules of surviving species. The fossil record warns against that assumption repeatedly. But ancient organisms were often not larger versions of living ones. They were stranger. The mainstream geological case remains strongest at the level of mechanism. Columnar jointing is real. Cooling magma does fracture into prismatic columns. Basalt flows and intrusions around the world prove it. Erosion does isolate resistant rock. Differential weathering does produce mesas and buttes. None of that should be ignored. But what it fails to explain, at least not comfortably, is why so many explanations stop at the process and avoid the pattern language of the form itself. Why are some structures so aggressively stump-like in overall geometry? Why do some natural remnants present clean, flat truncations and radial surroundings that call to mind a severed biological axis rather than a random survival of harder stone? And why do descriptions become vague precisely where resemblance becomes strongest? The official explanation may be broadly true and still incomplete in specific cases. Old photographs make the unease worse. In 19th century survey images, certain formations appear not merely tall but surgically out of context, standing above stripped landscapes with almost no transition from plane to vertical wall. There is often a sense of removal, as if the surrounding terrain were the aftermath of extraction or exposure rather than the ordinary setting of a mountain. Early observers used improvised language because they had to. Lodge, tower, monument, chimney, butte. They named by resemblance before they named by theory. That sequence is revealing. First came the eye, then came the category. What changed was the explanation. But the record also shows that geology itself was not built all at once. 19th century surveys classified by visible form, by practical mapping need, by mining value, by state boundaries, and by whatever theory could organize immense territory fast enough for use. A landform that could be listed as an igneous stock, erosional remnant, volcanic neck, or sedimentary outlier did not need a deeper answer to enter the archive. It needed a box. Once in the box hardened. That is how bureaucracies preserve uncertainty without admitting it. A description becomes a doctrine through repetition. The record is still there, so is the original ambiguity. Look next at what surrounds these structures. Many alleged stump-like formations sit in regions rich in coal, lignite, petrified wood, silicified roots, and sediment loaded with plant history. Thus, that does not prove they are botanical remains. But it places them inside landscapes already shaped by buried biomass on scales industrial civilization has spent 2 centuries extracting and burning. There are places where upright fossil forests have been found in place, their bases still rooted in ancient soils. There are petrified trunks so heavily mineralized that they read as stone until cut and polished. There are bands of iron, silica and ash that speak to burial, replacement and transformation rather than simple decay. The boundary between wood and rock is not philosophical, it is chemical, and chemistry can erase identity while preserving form. There is another detail, smaller but persistent. In many of these formations, the upper surface is treated as incidental, but it may be the most important clue. Most flat tops are usually explained as resistant caprock. Often that is correct, yet in the hidden history reading, the cap is not incidental. It is the wound. It is the exposed cross-section of a vertical body removed from its original system. Even when erosion roughens it, the overall logic remains, an axis terminated. A summit that does not culminate, but ends. The distinction sounds semantic until you look across dozens of cases. Then the same geometry begins to feel less like chance and more like repetition. At this point, the theory either expands or dies. If it applies only to one famous tower, it is weak. If the same visual and structural signature appears across regions, scales, and rock types, then at minimum there is a classification problem, and the pattern does widen. In the American Southwest, in parts of Africa, in South America, in Australia, and in volcanic provinces across the world, there are isolated columns, flat-top masses, radial escarpments, and massive vertical exposures that trigger the same recognition. Not all are identical, that would be suspicious, but they rhyme. Some resemble severed trunks, some resemble root crowns, some resemble broken limbs turned to stone. The pattern repeats through different geologies, which is exactly why it is so difficult to discuss. A single biological hypothesis struggles to survive contact with varied material, but the resemblance remains. That repeated resemblance is usually dismissed as pareidolia, the human habit of seeing familiar forms where none exist. There is some truth in that. Humans do see faces in cliffs and animals in clouds. But pareidolia is not an explanation when the resemblance aligns with measurable features, cylindrical isolation, vertical striation, radial drainage, flat truncation, and surrounding aprons of fractured material. At some point, recognition becomes morphological comparison. Science begins there, not after it. The question is not whether people can imagine a stump. The question is whether enough physical traits cluster around the same comparison often enough to justify formal testing, rather than ridicule. And testing is the part that rarely happens, not because of some grand censorship, more often because of institutional inertia. Geologists look for rocks, paleobotanists look for organisms, mining surveys look for extractive value, park services look for interpretable stories the public can absorb in a few paragraphs. Our anomalous forms fall between disciplines. If a structure is too lithified for biology and too shaped for comfortable geology, it is still safer to keep it in geology. Careers are built inside categories, not between them. Classification can hide as effectively as secrecy, and it does so without a single closed door. Economics may matter too. Entire regions depend on resource narratives tied to coal, hydrocarbons, mineral rights, and land use. Those narratives are stable because they are useful. To reinterpret even a small class of landforms as the remnants of biologically derived megastructures would not merely adjust a museum label. It would force new questions about the formation of coal basins, the history of biomass, atmospheric models, and the timelines attached to extraction geology. I'll say that does not mean anyone is suppressing the truth. It means the cost of asking is high and the reward is uncertain. Bureaucracy prefers questions with predictable outcomes. This is not one of them. There is also the problem of modern imagination. We are asked to picture ancient oceans, mountain building episodes, asteroid impacts, and ice ages, and we manage because schools taught us the images in advance. But a biosphere that produced trunk-like structures on the scale of hills or towers feels mythic before it feels scientific. The idea arrives contaminated by fantasy. Giant trees belong to folklore, paintings, and internet speculation. That makes serious inquiry harder. Not impossible, harder. Once a subject acquires the wrong audience, respectable institutions tend to abandon it. Even when the object at the center of the claim remains physically real and publicly visible. What remains, then, is not proof in the courtroom sense. It is a stack of stubborn observations. There is the shape of certain formations. There is the inconsistency and evolution of official explanations. There is the admitted existence of ancient giant vegetation, widespread petrification, upright fossil forests, and biomass-rich strata. There is the repeated visual logic of trunk, cap, flare, and debris. There is the tendency of institutions to preserve categories longer than uncertainty. None of these points alone settles the matter. Together they create pressure. Enough pressure to justify a different kind of question. Suppose, for a moment, that only a fraction of these structures carry a biological history deeper than their current labels admit. The implications would be unsettling, not because they are fantastical, but because they would force continuity between things we have carefully separated. Forest and mountain, wood and stone, fossil and landform, organism and terrain. We prefer clean borders. Nature often leaves none. The stone remembers, it keeps pattern after identity is gone. And this may be the most important point of all. Hidden history does not always disappear because someone erased it. Sometimes it disappears because the evidence survives in a form no longer legible to the system examining it. A stump becomes a butte, a mineralized trunk becomes an intrusion, a buried forest becomes a fuel seam, a pattern becomes scenery, then time does the rest. The explanation hardens, the object remains. So when people look at Devil's Tower or at a flat-top monolith on a desert plain and feel that the official account is somehow thinner than the thing itself, that instinct should not be dismissed automatically. Instinct is not evidence, but it can be the start of attention. And attention, if disciplined, can recover questions that institutions stopped asking. The hidden theory is not that every mountain was once a tree. It is that some landscapes may preserve biological architectures so transformed, so enlarged, and so bureaucratically misnamed that we no longer recognize what we are seeing. In the end, the argument is not really about a single tower in Wyoming or a single mesa in the desert. It is about whether our categories describe the earth or merely domesticate it. The official explanation gives us processes, the anomalies give us form, the archives give us uncertainty. The repeated resemblance gives us pattern, and the pattern does not disappear just because the theory sounds strange. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.